So it's a pleasure for the first speaker, Flavio Del Santo, to talk about realism, classical and quantum indeterminism. Thank you very much. I get to start from the beginning. I might thank the organizers, but all right. So this talk is a lot developed around the research program that we have with Nicolas Gisin since a few years already. You have heard from his side his talk, which was more focused on these different mathematical languages that we can use for indeterminism. And today I'm going to talk you more about some new recent ideas that we were developing, more on from the ontological perspective of what these indeterminism might lead us to think and develop. So let me just quickly recap once more from my side, what is my variety of indeterminism that I'm addressing today. So there is an orthodox, there is a standard way of looking at classical physics, especially which we have learned from our school books, that we have like physics is this kind of machine that evolves the stuff of the world according to certain laws, that in particular, if it was classical mechanics, they are ordinary differential equations of the degree 2, therefore they are like by their mathematical structure, they admit a unique extension in the parameter time, both in the future and in the past, given that they evolve a state. So the three parameters in the equations are the position and the velocity or the momentum, and they evolve these so uniquely in time if you have a perfectly specified mathematical point that is characterized by an interval of real numbers in both position and velocity. From this, we infer that our classical theories are deterministic. Historically, the way it's usually presented, although it's not very historically accurate, is that quantum mechanics was the first time where we started thinking. I would like to mention here that already like the so-called Vienna school of indeterminism of like Boltzmann and contemporaries of Boltzmann, in particular Franz Exner, already conceived before and beyond quantum mechanics the possibility of a fundamental indeterminacy in physics. But let's follow the standard, the simplified story that is quantum mechanics that kind of challenges the given view of determinism that was very well established at the beginning of the 20th century. And how does quantum mechanics challenge this? Through Heisenberg's uncertainty principle, that gives us a good reason in accordance to our empirical observations that you cannot assign a state with arbitrary precision in phase space, but you need to have like the volume cannot take a smallest arbitrary small amount of phase space, but it has a minimal volume that is that follow this relation involving the fundamental constant, the Planck constant, fundamental constant of quantum mechanics. And moreover, Bell's theorem has challenged perhaps even more this idea of indeterminacy, basically for the reasons that Tony has explained in his talk. If you remember that according to certain, so if you assume certain amount of assumptions, you cannot trace back so if you have a certain kind of independence of observation of measurements, you cannot retrieve determinism in a standard sense of deterministic causal connections. Okay, but then the state of our main theoretical framework seems to be this one. So we have never basically explored this. For centuries, there has been this idea that classical theory has had no foundational problems, interpretational problems in the sense of indeterminism. It had like this very clean mathematical structure and everything was quite neat in this direction. Whereas quantum mechanics, as I showed you, has these problems, and there is other interpretations, however, who would like to maintain a form of determinism, I would rather not talk about too many words interpretation in general, but for instance, Bohmian mechanics adds additional so-called historically hidden variables that complete the theory such that you can reconstruct the trajectories in a deterministic way. So we are in the quantum debate, these new events, these new observations, somehow heuristically at the beginning, then well structured in a theory, but led to a fierce interpretational debate on how to regard indeterminism in quantum mechanics. So my motivation, at least for this idea, is at least the very least motivation is an exercise of curiosity, whether we can actually go back and see that it's just a historical accident that we accepted a single interpretation of classical mechanics, and whether we can actually find some different interpretation that would move away from the standard view of determinism in classical physics. One way to do this, and this was exactly following the work that Nicolas has showed you, is to impose somehow fundamental limits to the precision to which variables are determined. So there is this implicit assumption when you say the length of this object is a real number. You're implicitly assuming that although it might be epistemically not fully accessible, but you can approximate, but you have like the idea that there is a true value of the object that is infinitely determined. If you impose a principle of infinite precision, so if you get away from this view of infinite precision, you can relax it and instead impose something that we call the principle of finiteness of information density, such that finite volume of space, or maybe of space-time, can contain only finite amounts of information. And if you do this, basically you reject the idea that any typical real number can be the value taken by physical variables. And this introduced some fundamental indeterminacy in your classical physical theories, such that even if you keep the same dynamics that I was mentioning at the beginning, you can basically shuffle around this and make this uncertainty grow, for instance, in plugging into some chaotic dynamics. You can enlarge even this uncertainty, leading to the openness of the future, because you don't have anymore a single trajectory, but you have like a whole bunch of trajectories that can be, in principle, be made as complex as you want through the right choice of dynamics. So somehow you can see so if you look back at this table, somehow this is how historically quantum mechanics developed, and then somebody in 1952 found out that you can add hidden variables to complete deterministically the theory. What we're trying to do is like somehow regarding that this interpretation was always completed, tacitly completed with additional hidden variables that would make the theory perfectly well defined. And if you remove this perfectly well determinedness, you can go back to an indeterministic view of classical physics as well. So this is a quote from Cézanne. One could add supplementary variables to alternative classical mechanics, which is our idea, in order to restore determinism. It suffices to add the mathematical real numbers to somehow retrieve determinism. And this is a picture, something that I showed you at the beginning. You have an infinitely precise point, but instead, if you add this kind of not at the moment well-specified finite volume in phase space, it leads to this alternative indeterministic classical physics, which I remind you, it resembles very much quantum physics, except you don't have a fundamental constant. How constrained is this volume? It's just enough that it's finite. And perhaps if you add, well, it could even perhaps be shrinkable to an arbitrary precision, but it must always remain constant. This is the only constraint that we put. Yeah, so if you remove the determinacy in the initial conditions, this leads to an indeterminism in general for the future and also the past. Okay, so this is the more general program, and now I want to talk about a paper we are soon to put out, maybe your, hopefully your meeting. Yeah, which is a new view that we call about all this potential realism. Okay, so let's start again from thinking about what what we want from an indeterministic theory. I will kind of constructively go through our way of thinking about this indeterminism. So an indeterministic word, in our view, is something that is able to produce non-necessary event, but not by necessity. It's a word in which new information actually gets created, and somehow this is related to some form of passage of time. There is at least a well-defined sense in which you have a before and an after, because you have an event that was not encoded anywhere in the universe that you could retrieve exactly whether this will happen and when this will happen, but you have this kind of clear-cut event that is at least distinguishing from a before to an after. Is a new information that gets created, as is illustrated in this very sophisticated animation. And one way that many people, when you tell people this, they say, okay, but the world is not fully random, right? Like, okay, you introduce these random events, but you see irregularities everywhere. How can you explain this? So we're not advocating for a fully random world, but rather this indeterminism can be associated with well-determined potentialities that can bear various strengths of whether an event is to happen or its mutually exclusive alternative is to happen. So we think in this in terms of potentialities. So to recap again, the classical physics view, a state in classical physics is a system, is a system's maximal or complete set of intrinsic or possessed properties. So you define an object by the relevant properties. You associate a possessed amount of properties that actually define the individual object, and this is its state, pure state, if you want. Really, there is no more to know. There's a maximal amount of information you can have about an object. And so outcomes of measurements in this kind of theory are manifestations of actually pre-existing, well-determined properties. And states are the collection, full collection of these actual values possessed by the objects in the form, in the mathematical form, usually of n-tuple of real numbers that are given, are assumed to exist at any instant in time, fully defined, fully determined. In our view, that we call potential realism, outcomes, as I said, are dynamically realized. Now they separate the instance of time from before to after. They create new information. And how do they do this? They create new information from an array of exclusive potential outcomes. But before the realization of one of the outcomes, the element of reality, so what we now call the element of reality, is not anymore the collection of the actual properties, but is the collection of the potential properties associated with each, in general, still indeterminate outcome of a physical degree of freedom, for instance. So the new pure state is a collection of entities that encompass the potential of realizing one of the properties. How do we want these potentialities to be able to make physics with them? So we want them to be carrying the causal structure of the events. So we want to enforce causality. We want this not to be just epistemic, some epistemic form of uncertainty, but we want them to be actual objective causal connections that with the constraint on not being governed by necessity. So they are causal connections, they encode the causal structure, they are objective, they are just a physical thing, an observable thing, possibly, that describe indeterminism. And we call this from, quite a vast literature quite confusing that started in the last century, propensities. So don't think that propensity, I will define them in a more detailed way in a second, but when you see propensity, don't do and think of the standard view of like Popper and propensity. Of course, they're inspired from them. They share a lot of ideas of many people who work on propensities, but we believe that propensities have been like stretched in many different directions, but with a lot of formal and interpretational problems. So first of all, we don't think of propensities in terms of objective probabilities, as I will explain in a bit. So don't think necessarily that these things are mathematical probabilities. So what are propensities? I will give you first somehow an intuition of this. There are tendencies of an event to happen. For instance, the outcome of a measurement, given the relevant causal conditions that can influence these particular events. However, they don't do it in a necessary way. So you have to imagine them as some kind of potential force or the weight of something to happen without being necessarily done. And we believe that this is a very natural way of describing a causal indeterministic word instead of having actual properties you associate to the propensities in general. It's the new element of reality that we postulate. So our propensities have at least these properties. We want them to be single case. This has been a big division in the literature about propensities because some scholars have thought propensities as being a property of a whole sequence of events. So upon repeated measurements, when you finally draw statistics and you can build basically a probability distribution, if you want, that is the propensity. Somehow is a non-local in time object, but we believe instead that propensities are really somehow a law that causally connect two single events, so our single case or propensities. And I think that you need this kind of single case propensities if you want to have really a fundamental indeterministic theory that doesn't depend on an arbitrarily long, possibly infinite amount of repetitions, right? They are intrinsic properties of the system together with its, again, causally relevant conditions. So it's what there is to know about the system. It encompasses everything that can happen given everything that happened in the past. And as I said, they have this idea of causality to the extent that they quantify a degree of objective possibility. So you can see them as some kind of an indeterministic law or a potential force that guides the events to happen. And we postulate them to be real. Like we talk, I will elaborate more on this in a moment, but we talk about them in the same way that Tim was talking about the wave function for the guiding function of particles in movement mechanics. Is something that maybe is unobservable, but you can have like indirect observation of this kind of things, evidence of this kind of things. Just to relate them quickly to causality and time. So this can be the E's can be any kind of events, and you can really see propensities as constructing a graph of all the possible causal events. And it's actually a multigraph in this case where you have like these red arrows are the things that do happen by necessity or have happened in the past, perhaps. So this was at a certain point, this was an open future, but as time progresses, only one of two possible or n possible outcomes get realized. And so propensities indirectly define the concept of present as a slice or a manifold that in the causal graph separates the events that have already been actualized, therefore evolving to a propensity of 0, 1, to the propensities that are in general between 0 and 1, any possible outcome. So this has to be seen as the quantitative strength of a possible causal connection, right? So if you have a half propensity, it means like that you will see statistics where half of the time one event will happen and half of the time the other. or you can have all the possible intermediate values where one event is more propense, more likely to happen. So it's really a measure of objective likelihood for an event to happen. Perhaps this slide is unnecessary in this conference, but I'm gonna say it nevertheless, that we just have a very nice discussion on realism, and in certain circles you have to justify why you want to add such a thing like an ontology to your theory. And I deem metaphysics to be necessary for the understanding, and science could be able to explain and therefore to make us understand. So I think the metaphysical elements in the form of an ontology for a theory is something that you have to introduce, because you have to specify what are the things of the world you're talking about. So for me, these propensities now in this particular model, well, in this particular worldview, is what I call the real elements, the elements of reality. You have these kind of entities that live somewhere in the world and actually influence the things that we can observe. So yeah, each theory necessarily comes with some ontological position, even the negation thereof, if you want to be like very strict. And okay, and I contend that each ontology has a cost somehow. And of course you have to it can be a matter of guiding principle of a single scientist. It can be many reasons to choose an ontology over another, but you have to see what is the cost of your ontology. And for me, like I have two trivial examples here, like Anaxagora had the seeds, there were like in each body there was a microscopic elements of all the other bodies, like miniaturized versions of every possible object and element was forming the other objects. So in the human body there would be tiny whatever trees and tiny anything that happens. So you have an ontology that can explain things. You have a consistent story to tell, so it's an explanatory theory, but it's very costly ontologically, because you have to invent as fundamental elements of reality. You have to postulate an immense diversity of these things and put them together, squeeze them together to create what we observe. And same goes for the absurd inflation of required word in the many word interpretation. For instance, it's a story you can tell, but you have to buy that they have like this immense amount. The word is splitting every time something happens, basically. Okay, why I'm saying this? Because I consider potential realism a good ontology in my view, because I find it a very economical ontology. What we observe in the world, and we ever only observe this, is statistics. So since science started, our observations are always statistical. Classical physics, even if you can postulate this single real number, what you do is that you go there with a ruler and measure 100 times, and then you do a Gaussian with error bars, and you propagate the error of whatever you want to calculate with this. So we always only had the statistics and associated probability distribution to it. So having an ontology that by its intrinsic nature is basically mimicking the same things that we have always observed, it seems to be a minimal ontology that at least is you're taking seriously what we're able to measure, and you give an ontological weight to it. And on top of this, it doesn't seem to, people can ask me now, okay, but you're postulating this unobservable thing where it lives. Is not very different from what we do in standard, even classical physics, because by postulating that it exists, a real number that is associated to a certain measure, you are only, what you measure is exclusively repeated tentatives with different instruments or many observations with the same instrument that is in accordance to what you have postulated there is done there. And propensities can be measured exactly in the same way. You can have an ideal measurement and repeating it many times that will converge to a certain frequency of observed outcomes, and then you can postulate that this is approaching something that is living out there in the same sense of a real number. So it doesn't have more more strong epistemic inaccessibility than the alleged real value of a normal measurement. Okay, so let me go a second now to the more formal part of propensity. So I told you that propensities are an element of reality, but propensities are also usually taken to be formalized at the mathematical level by a probability. So this was how they were actually invented by Popper and others. And it's usually considered like at the mathematical level described by probability. There is a quite famous in philosophy, there is a quite famous called paradox, Humphrey's paradox, that can be casted in the following no-go theorem. In fact, Leslie Ballantyne called it a theorem because it follows logically from its conditions. That it actually doesn't have any paradoxical feature. It just leads to a contradiction from some taken assumptions, like a no-go theorem. And the assumptions are the following. Propensities quantify indeterministic causal connections in the way that I have explained so far, that you have this kind of potential forces that connect one event to the causally associated one with a certain strength. And that probabilities are propensities at the formal level. In particular, they satisfy the Kolmogorov axioms from which one can derive the Bayes rule. And now this is the proof of the theorem. Not very sophisticated. That's a very the simplest example you can give to violate the theory. To find this no-go theorem is the following. So you take the Bayes rule, and you know that you have a certain propensity of an event given its cause. But if this thing follows Kolmogorov axioms, you have a Bayes rule. So you can formally write the probability of a cause given its effects as a function of the individual probabilities of the effect and the cause to happen, right? Now, if you impose, this is very well known, at least in the GPT theories, it's a way to impose causalities that you don't want. If you take something that you believe it's an effect of something else and you condition the cause on its effect, you don't want the cause to depend on its effect. You want to have a directed way of thinking of cause. You call something a cause because it cannot be influenced by its effect. And so the probability of a cause given its effect must be only the probability of the cause. Okay, you plug this thing into here and you will see that probability of the effect given the cause doesn't depend on the cause anymore, which leads to a paradox from the assumption that this cause is actually a cause, is a trivial, is a non-trivial, there is a non-trivial causal connection from the directed connection from the cause to its effect. So this very simple calculation shows that by the very way you construct probabilities, you cannot insert a causal structure inside the probability calculus, because the probabilities are actually built to be, so a joint probability distribution, this comes from the fact that the joint probability distribution is symmetrical in its argument. If you take probability of event A and B is the same with the probability of B and A. The sample space from which you draw the events doesn't have any causal structure embedded into it, and this shows that cannot have any causal structure embedded into it if you want to maintain the probabilities as they formally are defined by Kolmogorov axioms. Therefore, the story goes that propensities cannot fulfill all the axioms of probability calculus. However, so in this, many different authors try to solve this paradox in different ways, and only a few still consider propensities to be causal. That's one of the ways they introduce these long-run propensities, because in that case, it's not a causation of single events, but it's kind of a huge time non-local object. But if you want to maintain what we want, you have somehow to relax the axiom of probability. So the propensities need to have their own axiomatization, but they want to say something that is, they cannot also differ arbitrarily from probabilities, because if they want them to be describing to be somehow empirically adequate for what I told you for an indeterministic physics, they have to be compatible with observations. So you need propensities to be somehow limiting cases of series of observations in the same way that probabilities are. So propensities and probabilities are connected for sure, even if they're not the same thing, through at least the law of large numbers in many repeated observations. You also want propensities to be able to tell certainty and impossible cases. Therefore, they are bounded from both sides, and you can assume them to be in the interval 0, 1, in the same sense that probability are, because you want, it's a measure, it must be a monotonical measure of likelihoods, right? So you want this to be bounded between a 0 and 1, like probabilities are. And if you want propensities to be able also to, at some point, it's not fully developed by anyone that I'm aware of, but if you want propensities to be, this potential realism to be applicable to any theory, including quantum theory, propensity require to be no local from best theory. So you have to impose this further constraint when you build your propensities that they're able to at least generate randomness or generate indeterministic events at different locations, possibly space-time separated locations that are correlated. If they generate a non-deterministic event, they can generate multiple of them at different locations. And the fact that these propensities and probabilities are not exactly formally the same, but they have to share at least these things, have been noted before in the literature, and Gillis in his book on probability foundation, philosophical foundations of probability. He calls propensities a non-Kolmogorovian probability theory by analogy with a non-Euclidean geometry, in the sense that you maintain most of the structure like a non-Euclidean geometry does with standard geometry, but you have some to relax at least one of the axioms and you to re-axiomatize it such that still they're very similar. Okay, I think I'm going to skip more or less this. I just want to say that this is something that Nicola has shown already, but we used propensities to actually find a model of indeterministic classical physics, where we call these fixed finite information quantities. So you remove the real numbers and you substitute the initial conditions where the physical variables take value in these finite information quantities that are just a collection of propensities of all the possible digits that you can measure. Okay, and so it's not anymore, when you measure the length of this table, is not anymore one single real number, but what you have, what you associate to this is a list of propensities, and up to a certain amount of digits, these propensities are 0 or 1 because you have determined already this amount of digits, but the one down the line are not yet determined. And now I'm going to elaborate a bit more. So yeah, this is back to the initial motivation of the project, and we actually have one specific way of expressing a non-deterministic classical physics in this corner up here. And I'm coming to a conclusion that I think is very interesting to be discussed, which is, it seems from what I told you now, and if you haven't realized yourself, I hope that convince you now, that every fundamentally deterministic theory has a sort of a measurement problem. Since you have elements that are not yet determined, not yet determined in, for instance, what I was telling you, the length of this table, I still want to be able to measure the length of this table up to the precision that I decide, up to the precision that the measurement apparatus I build for this purpose determines. So you want measurements still to have to be the ones we have known forever in science. Therefore, you want a certain form of stability. If I measure multiple times an object, these measurements should be up to the experimental error. You want them to be compatible. You want intersubjectivity, that different people, so there must be some kind of objectiveness into what these digits have been measured. And you want, most important, you want precision in probability. So if I have a ruler that it has the order of 1 meter for this thing, I can say it's between 0 and 1. But if I tomorrow come with a ruler that has the tens of centimeters of precision or the micron of precision the next day, I want this piece of wood, when inquired, to reply uniquely, even if I was telling you that perhaps not all the digits down the line are yet determined. So there must be a mechanism that tells you how, when, under what circumstances potentiality becomes actual. Because you want at least that when you inquire, you force it to give you a reply, in the same sense that you have a quantum measurement problem. When you go and measure in a certain basis a spin, you want it to collapse of non-Lagrange states. You know that this is what's going to happen. You don't want this, you don't want superposition to remain after you have a measurement. That's the definition of a measurement. And here you also want to extract a single definite outcome when you measure something, even if it might be indeterminate before the measurement. And so different interpretation of quantum mechanics, we have been like, we know very well that they have different, they give different explanation solutions to the quantum measurement problem. And I think you can draw more or less a one-to-one comparison of different classes of explanations in quantum mechanics with this classical measurement problem. So one way is, for instance, the Copenhagen interpretation. Copenhagen interpretation, although it's not, well, it encompasses a huge class of different ideas, more or less have a core of ideas that the measurement is imposing the collapse to some extent. It could be an extreme case where is the consciousness, or it could be just the size of an apparatus that is a macroscopic object that is coupled to a quantum object. But there is somehow a form of collapse that is imposed by a higher level of description. And this you can think it in the same way that I was telling you that when you go with a ruler, there is some mechanism that is like imposing as a sort of, so these are, unfortunately, Barbara Drosser could not join the workshop, but she would, together with George Ellis, they have this top-down causation explanation of the quantum measurement problem, where you have different levels of descriptions. And in this case, the different levels would be like when something very determined coupled to something that is not yet determined is imposing the same level of determinacy. And this mimics what happens in the Copenhagen interpretation, where you put experimental apparatus on quantum state. Objective collapse theories, of course, it's very, you can think that propensities evolve in time dynamically, and then from time to time, as time passes, that's exactly what I was telling you at the beginning, is really the clicks of this new information appearing that happens at the determination of single events or single digits that spontaneously happen. And maybe you have a mechanism for which, if you couple something, the dynamics of this propensity gets is made faster, in the same way of VRW when you couple to a big body, macroscopic body, to a quantum system. I've started from Bohmian mechanics. So Bohmian mechanics would be the same of like doing the standard classical physics to the propensity, the potential realistic interpretation. You just add the real numbers and you complete all the numbers at once. So you recover the deterministic explanation. And finally, you can even think of a many-word interpretation of this potential realistic in classical indeterminism, in the sense that you reject the hypothesis that I always take for granted, that when you measure, you actually have one single outcome. But you can think of this graph I showed you of propensities as something atemporal, that all the possible outcomes do exist. And so when you measure, you're just following one path of the propensities, and you kind of have, instead of the wave function of the universe, you have the propensity graph of the universe, and you don't actually, time is not passing by selecting a single outcome of determining a single outcome, but they all happen. I don't know. Maybe I don't go too much in this area. So a bit of was going to be my conclusion somehow, that I find it is interesting that by exploring the foundation of classical physics, somehow you go to to dig out some problems that were given like always as solved because you actually didn't pose them historically within classical physics. And by posing them, you see that many of the problems that we believe to be peculiarities of this quantum mystery that we keep discussing, like quantum mechanics has introduced for the first time fundamental indeterminacy that could not be the case in classical physics. I think it can well be the case, and we have found, well, there is this is one way I showed you to express how you can have this fundamental indeterminacy in classical physics. So in fundamental indeterminism is not uniquely quantum. This leads to a kind of measurement problem of the determination of single outcome out of potentialities. So this is also not uniquely quantum. And then you have this plurality of interpretations to resolve the measurement problem. That is also a discussion that can well be held in classical physics. So it's also not something that belongs exclusively to quantum. So what do we leave to the pure quantum physics is at least that well, there is a big difference, of course. So I'm not claiming here that, so take this a very highlighted last point. I'm not claiming that classical physics is quantum physics, because quantum physics, as I showed you, has the unique feature of having incompatible measurements that are related by this new fundamental constant h or h bar, where that appears in the uncertainty principle and also appears in the violation of best inequalities, because you cannot achieve it without incompatible measurements. Thank you.
Thank you. That was really cool. I think I have a question about propensities. I'm going to try my best to make my question clear, but it's not clear to me either. So sorry about that. So
let's work it out together.
let's find out. No, I think my question is about how propensities in specific cases relate to probabilities. And I think you went through that already, but I think there's something I never understood about how propensity work.
Yeah.
Which goes something along the lines. So suppose, should I think that if I have like 50% of finding, you know, the spin up in a measurement or spin down, in the propensity words corresponds to there being something that goes 50% of the cases up and 50% of the cases down. Is it something like that?
Like something like what?
Yeah, I mean, I'm not asking about the authority, but I just wonder, like, because there seems to be a principle needed that relates, you know, there being something that has the, I don't know, a degree of instantiation of the propensity. Okay, or I tend to think about this position. Maybe I'm mistaken, so this is also part of the question. But if it's the disposition of being deflected upwards and the disposition of being deflected downwards, and
so you would like to have like a field of something.
No, I'm not asking about the ontology, really. I'm just trying to understand, is there a bridge principle linking this property of, you know,
disposition? It's really disposition. So
okay, but what tells me that the disposition, okay, suppose instead of having 50-50, I have 75 and 25.
Yes.
This makes it a little bit maybe more cogent, my problem. So should I think that having the disposition to 0.75% and 0.25 relates to what I find. So out of me finding 75% of the time one thing and 25% of the time the other thing. So the degree of instantiation of the disposition is related to the probability of finding a certain outcome, right?
Well, probably to the statistic, let's say, of
yeah, okay, but yeah, but what tells me that, you know, like suppose I have like an object that is 0.95 spin up in one axis and 0.005 down in the same axis, and they have like the disposition of behaving in a certain way if I measure it, being deflected that way with 0.95 and so on. But what tells me that the degree of instantiation of the disposition is related to the problem, to finding, to the statistics. What tells me that? You see what I mean? Like it could be that if it's always like, if the object has 0.95 degree of being up, then I will always find it up. If it's 51, that's already gonna be enough to find it always up. You see?
Yeah, of course, we are postulating that there is this single disposition. There is disposition in the single run. This cannot.
And this
cannot be.
And this is related to the probability. So the degree of instantiation of the propensity is mapping the probability.
Well, it's mapping the likelihood of something to happen. So if you manage to find exactly the same causal conditions under the same idealized measurements, then this could give you an estimation, like it should approximate the actual tendency of what's happening. But in the single run, you have to believe it, like it's the ontology of the thing that tells you that. But so is in quantum mechanics. You have to assume an IID assumption of some kind if you want to do an experiment, like even to find the interference pattern. You cannot, if you launch a single particle in any quantum experiment, it doesn't. You cannot discriminate from having a statistical.
No, I think it's a fair assumption. I mean, it's a fair assumption, but it's just that it seems that in this case, it's when you take very serious, and then I'll shut up, sorry. When you take very seriously dispositions and propensity, there's still a step to be made that is not always clear what justifies it, that links the disposition or the degrees of instantiation to the probability, because that doesn't come for free. That's not the only thing.
Well, that comes from the law of the large numbers.
Okay.
There's also Greg who has a question.
Actually, actually, I had a comment. About your very last point about the fact that there's no incompatibility of measurements in classical case, that's not completely clear. And there's very interesting views on that were expressed by Nikolai Krylov back in the 1940s. So his was the work that inspired Yasha Senai's work on ergodic theory in justifying statistical mechanics. So Krylov was a very innovative pioneer in statistical physics, and he had a view expressed in his early work. Unfortunately, he died before he could work a lot of this out, but he believed that there was a complementarity also in statistical physics between the microscopic point of view and the macroscopic thermodynamic point of view. So for example, you couldn't simultaneously measure all the positions of all the particles and the momenta and simultaneously talk about macroscopic observables like temperature or entropy. And you might want to take a look at he has a book of his papers that he published in 1940s, edited by Senai, called Foundations of Statistical Physics, in which he was arguing that there was an analog of the uncertainty principle also for classical statistical physics.
Can you give us the name of that guy?
Krylov, Nikolai Krylov, Krylov. So Foundations of Statistical Physics.
Thanks a lot. That's very, very useful hints. I'll surely take a look, because I also believe that something can be done to find some kind of analogy, if nothing else, between the incompatibility.
Greg,
Yes.
in this interpretation of somehow a not simultaneous measurement of the micro variables and the macro variables, is that not the interpretation we're supposed to give to multiplicity?
I'm sorry, multiplicity?
Multiplicity of a given macro state, the number of microstates that correspond to the macro state, that those in the classical theory can be measured at the same time, right?
Well, I mean, so of course, yes, absolutely. I mean, if you take the Boltzmann entropy, that's just the number of microstates compatible with the given macroscopic state.
Yes.
but
So
I
this
can only.
goes-
So I mean, I'm not saying that I understand Krylov's views.
All right.
Okay, I'm saying that they have been proposed, and it's a little bit of a mystery because he died during World War II. Before he claimed that he was in the middle of writing papers trying to justify this point of view, and so you can only get glimpses of what he had in mind.
All
in the
right.
book.
Oh, that's too sad.
Yes.
Generally, proposals that come from you tends to be right and interesting. So I'm paying attention very carefully, even if you say you might not agree, but it's if you're mentioning it, it's because it's got some interest to
Well,
my experience.
I mean, Krylov was a serious guy, and he was the person that came up with the mathematical ideas that Yashas and I used to prove ergodicity of the hard sphere system. In fact, this was all based on the mathematical analogy that Krylov understood between geodesic motion and Hamiltonian mechanics. And
All right.
so he was a very smart person, but unfortunately he died before he could elaborate these views about this complementarity that he argued should exist between microscopic and macroscopic. So
It sounds like something worth chasing. What his motives might have been.
Thanks a lot. Maybe another quick question about team.
So let me just make two, I want to make a quick point and then ask you a question.
Yeah.
I can see that there is a parallel problem to what you might think of as the measurement problem. I'm not sure you want to call it the measurement problem, right? Something like the realization problem or the transition from potentiality to actuality. Right. So something has to happen,
Yeah.
and you'd like some specification about it. Whether it's connected to measurement or what that even means.
Indeed, yeah.
I mean,
And measurement it gets amplified as well,
Right.
because you want to get a response when you inquire, right?
right, and you have kind of the same issue. I mean, you put the top-down stuff together with Copenhagen, and that seems right, because on the top-down view, the top thing better be actual.
Exactly.
And then you wonder how that came about, right? Then you get into this infinite regress issue unless you do something else. But the question I have is this, even if I can understand, if you see in the world empirical, kind of stable empirical frequencies, right? Observable frequencies. One option is to say, well, maybe I've got a propensity here. Maybe I have something fundamentally indeterministic. There are different strengths of propensities, something like that. But everybody has to realize that sometimes we see very stable frequencies, and we know that isn't the case. And so this is the example, as I say, coin flipping. If you or I were to flip a fair coin many times, I can predict and be correct that we'll get just about 50-50. But we know from this device that Diaconis had built, right, that it's effectively deterministic. So in any case, there has to be another scheme for explaining those robust observed statistics that doesn't require a propensity. I'm not saying you can't put one in, but you are going to have to at least do the work also of understanding how those come about in cases where we're really sure the underlying dynamics is effectively deterministic, right?
Fair enough. I mean, two comments on this one, and then I conclude. One is that for me, like indeterminism in this case is, I even have a slide, I think, but it's a sufficient condition.
Yeah.
So it doesn't mean that if you have like certain things that the oscillator have like not 50-50 or 0-1, the certain statistics, we observe very stable things and we can explain that deterministically, and that's totally fine. For me, it's like it's enough that there is one event that is not predetermined that we can talk about this. So that is, it makes sense to quantify it and to find an element of reality associated to it. And the second thing is like what I wanted to say is that we still always have epistemic uncertainty in the case of the coin. So it's very difficult to disentangle. That's why I have to define these propensities, and the way to uncover the propensities in the draft of this paper, we have to define them through idealized measurements where you have like noise-free measurements. Yeah. So somehow you have these two different levels, but I'm I'm happy to see it as you have this underlying causal indeterministic connections that are propensities, and on top of that, you can build your whatever form of uncertainty that can be quantified. And at that point, probabilities are good.
Yeah.
Because they're not causal, they're just establishing correlations between facts. They don't have a causality into probability. So, but somehow they can or not be determined by the propensity itself or by some uncertainty. So that's the tricky part that I admit. Thanks. Okay, so thanks.